So this short paper is about an numerical algorithm to obtain analytic solutions for the continuum forward kinematics problem of deformable linear. This is essentially the problem of describing the shape of a cable, tube, some deformable rod element given the terminal end, the pose of the terminal ends. And the application that we have in mind is, of course, the handling of such elements, where we are giving the end-effector pose in the case of dual arm manipulation, or just one end-effector pose and the fixed position and orientation of the elements. And there is a whole bunch of literature on this. The basic idea is to be able to describe the shape of this DLO, this deformable linear object, rod cable, or whatever it is, by knowing the pose of the two end effectors. So inferring the shape of the element by just knowing the end effector poses. And there are different ways of doing this. There are kind of analytic methods, and also there are numerical methods based on, for example, machine learning approaches. What the problem here is exactly as I was saying, the geometric problem we are addressing. The task is to ideally in closed form describe the shape of the element by just giving of course the material parameters we need to know about the element that we are manipulating, of course, and also the terminal ends. And this not only is important for the dual arm manipulation of these elements, but also for continuum parallel robots or continuum in general. So the setting in which we are working is that we consider the rod as a continuum, and in particular either as a Cosserat-Reissner continuum, so to say the micropolar theory, or as a Kirchhoff rod. And that means that we are considering the cross section the cross section as a curve in SE3, and the Lie group SE3 as a metric space, and the cross section is then described by an element, let's say a homogeneous matrix. This is usually used for representing it in terms of a path parameter. And of course, we need to parameterize it. There are different ways of doing this, like Cayley-Rodriguez parameters or any other non-canonical parameters, but we are using the exponential mapping to, in the end, use the capital X here denotes the screw coordinates, on SE3. So the Cosserat-Reissner rod is the most general kind of rod that you could imagine, and the kinematics is described by introducing some sort of a deformation measure, which is called chi here in this case. And this is, of course, the corresponding six vector comprises the torsion, bending, curvature, and also the shear and compression. That's nice, but in most of the cases in application scenarios, we don't have shear. For the Cosserat-Reissner theory, what we already have a very efficient algorithm to infer the shape merely from the known end effector poses or the terminal poses. So this is a nice thing. It's going to appear hopefully in what is it, automation letters. The Kirchhoff rod is then a special, or let's say a constrained version of the Cosserat-Reissner rod, in a sense that we have to satisfy a constraint, and this is a geometric constraint, which simply means that the shear and compression is non-existing, which means that this vector rho that we had at the beginning is equal to 1 to the unit vector E1 if you have the frame oriented accordingly. And then the kinematic reconstruction equations, they reduce to this set of equations, and this is a decoupled system of equation, because the first one deals with the torsion and the bending, whereas the second one is just the result of the first one. So we have essentially reduced this system to a reconstruction on the direct product of SO3. And what we do is to this algorithm to invert to compute the pseudo inverse of the Jacobian. Finally, a first experimental result that looks also very promising. With this, I would conclude. So essentially, what we have an explicit way of describing the analytic shape of the linear deformable element, and to improve the accuracy, there are two ways of doing it. We can, and this is what we also did, to use multi-segment approximations, but also we can increase the order of approximation. And this is what you see, for example, the fourth order is, for example, then given by this equation.